Next up, equilibrium. Mostly, a chemical reaction is going to start and then finish, or it's not going to start. That's the way chemical reactions usually work. But sometimes, under very special circumstances, a reaction can reach equilibrium, which is a state of rate balance between two opposing changes. Here's an example of a rate balance. You spend money as fast as you earn it. You cut your hair as fast as it grows. You cut your fingernails as fast as they grow. You walk forward on a treadmill at the same rate the treadmill is going backwards. You go up the down escalator at the same rate the escalator is going down. What does that mean? Looks like nothing is going to change, but you have to constantly change stuff to keep everything in balance. For example, in a chemical reaction, the rate of synthesis equals the rate of decomposition. That would be equilibrium. N2 and H2 combine to form NH3. That's this forward arrow here. But the NH3 decomposes to reform nitrogen and hydrogen. That's the reverse arrow. Usually, it's either going to be that reaction that happens, or it's going to be the other reaction that happens. At equilibrium, both reactions happen at the same rate. That's why we have a double arrow to show that the forward and reverse reactions are happening at the same speed. Solution equilibrium, which takes place in a saturated solution where you can't add any more stuff to it. The rate of dissolving equals the rate of precipitating. When you dissolve salt in water to form a salt solution, the rate of dissolving is going to be faster when you first put the salt in. But as more salt goes in, some of it starts to reprecipitate. When the rate of dissolving and precipitating are equal, your solution is saturated and it's at equilibrium. Phase equilibrium, where the rate of melting equals the rate of freezing at the freezing point, which is the same as the melting point. Water turns from a liquid to a solid at the same rate that it turns from a solid back into a liquid. When you put an ice cube in water exactly at the melting point, 0 degrees Celsius, the ice is going to melt at the same rate that the liquid water freezes. So it's going to look like you're staying with exactly the same amount of ice and liquid forever, as long as you don't mess with it. So those are your three basic kinds of equilibrium: reaction, solution, and phase equilibrium. The properties of a system at equilibrium, because it's a rate balance, anything you do that might change one rate over the other will mess up your equilibrium. So you need to keep the equilibrium in what's called a closed system. You need to keep temperature and pressure from changing, and you can't add any more reactant, and you can't let any product escape, especially gases. Put a cork on it, put a stopper on it, prevent anything from happening, and you'll keep that system at equilibrium forever. Now, it may not look like anything is happening, but when you're walking forward and the treadmill is going backwards, you're moving, it's moving. Even though it doesn't look like anybody's going anywhere, it's always in motion. It's dynamic. As soon as you stop moving, that treadmill is going to throw you off the back end of it. So you got to keep moving. You got to be dynamic. And a system at equilibrium will stay at equilibrium forever unless you do something to mess it up. This is a phase equilibrium when you can measure vapor-liquid equilibrium. Vapor-liquid equilibrium, where the rate of evaporating equals the rate of condensing. Now, as long as you don't add any heat to this, the equilibrium will stay the way it is forever. If you add heat, the liquid will simply boil off and you won't have liquid anymore. You don't want to cool it down. If you cool it down, the gas will condense into a liquid and it won't be at equilibrium anymore. You don't want to add pressure. You add pressure, you're going to force the gas to liquefy. You won't be at equilibrium anymore. You don't want to decrease the pressure. If you decrease the pressure, the liquid, because the vapor pressure is going to allow it to boil at a lower temperature, that liquid will turn into a gas. As long as you keep the temperature the same forever and the pressure forever, this system will remain at equilibrium forever. And it's dynamic because it's constantly in motion.